So now, if you've done your homology searching, or maybe even before you start doing it, you want to know how good your method is, right? So you need a reference. In the previous course, you've used Go or PFEM or SCOP to do that. A more strict way to do it is using direct structure comparison. And fortunately, you don't have to do that yourself. There is actually a database is called Homstrut. Sorry, did I say something the wrong way around? No, I heard somebody say structure. It sounded like I was saying it the wrong way around. Yeah? Okay. That sometimes happens. Yeah. Okay, so Homstrut is a database of homologous structural alignments. Right? So it does exactly what the name implies. So it has alignments of proteins with a similar structure, which are also, judging from the sequence, clearly homologous, right? So, but maybe not a priori easily to see from the sequence. Well, in this example, it is actually clear. Right? So, for example, here you can see that there's a gap here, but then there's like a conserved cysteine over here, right? And there's some more conservation. It's not about the details right now. Okay, so we're not going to go into all of the details of specific methods, but I just want to give you a recap of how to do the benchmarking. I'm guessing we can do that pretty fast because it's about log plots, right? So now if you do sequence searches, you have your query, you search through your database, and there's basically two types of hits you can get. You can get hits of homologs, which are then true positives, right? So you can get hits of non-homologs, which then are negatives, right? And then if you have what you're basically doing is you're given the information of your query, you're sorting your database so that the positives are at the top and the negatives are at the bottom. So if you set your threshold of your score somewhere, typically for an e-value threshold, everything above the line is positive. If it's correct, it's a true positive. If it's wrong, it's a false positive. It's not very difficult if you do it this way, right? And everything below the line you predict as not homologous, and then you're probably correct in most of the cases, and you'll be wrong in some cases. Yeah? Okay. So you can express this in what's called confusion table. Yeah, so you have observed positives and negatives, you have predicted positives and negatives. If they agree, it's a true positive or a true negative, if you agree on being negative. And if they disagree, it's either a false negative if you predict it as not homologous, but it was actually homologous, or it's a false positive the other way around, when you predict it to be a homolog, but it's not observed to be a homolog, right? Okay. Now you can elaborate this a little bit more. That's not really required in this case. Now, you've also, most of you have seen rock plots a bit, right? And this is how you build them, right? So you plot sensitivity or true positive rate versus specificity, or 1 minus specificity to be precise, also called error, or false positive rate. So whenever if you go through your ranked list of results, you can imagine that you're relaxing your threshold all the time. Every time that you get a true positive hit, you go up. When you get a false positive, you go to the right. Yeah. You never get true negatives or false negatives here. Why not?
There's a question.
Yes, that's a question. True positives go up, and false positives go to the right. But why don't you count true negatives or false negatives here? They're not in. Sorry, in what?
They're not in the homologs you found.
Yes, because you're predicting the positives, right? Which are either true positives or false positives. Yeah, and it's also what you're putting on the axis. It's the true positives or 1 minus the true negatives that is actually false positives, right? Okay, so now this is a different way of looking at that. If you have your scores for your negatives being the blue distribution and the scores for your positives being the red distribution, and you set your threshold, then for any given threshold you get a different mixture of positives and negatives, right? So if you shift it up, you're over here, you're not predicting much, but they're all correct. They're all correct, you're also not making many errors, right? So being correct, you're over here, making errors, you're over there. If you want to predict more, you have to raise your threshold. So you're going to predict more, which is correct, but you're also going to inevitably include some negatives, which is incorrect. If you want to play more with this, you can actually, sorry, I'm gonna switch to another window, but I have to switch between Microsoft and Linux, and Microsoft doesn't want to let go. There's actually some of these very cool online tools where you can play with, right? So now you can actually set your mean and variance for the two distributions. So you get two distributions here, the negatives and the positives. And over here you have the corresponding rock plot, and you can actually set your threshold at different places. So I have to try and catch it while being with my back to the laptop. So if you shift it, or you see the point here on the rock plot shifting along with it, right? So if you want to avoid making errors, you need to be here before the red distribution starts increasing. Yeah. If you want to include half of all positives, you have to be in the middle of your positives distribution. You have 50% true positive rate. You're going to start making some errors, right? If you want to include all positives, well, good luck doing that without errors, right? And you're not going to be. This is actually in biological data quite a nice separation. Yeah, it can be much worse. Yeah? This is it can be could be much better, but that maybe happens to physicists, but not to bioinformaticians or biologists. It doesn't happen. Okay. So if you want to get next year, I'm gonna use this for fundamentals as well for you guys to play, or not you guys, but next set of students to play around. Okay. The link to that tool is on the bottom of the slide. Right, over here. But if you just Google for rock curve demonstration or rock plot demonstration, then you'll find something. There are bazillions of these tools because it's not easy. It's not difficult to program it. It's quite easy. Okay, so so this is actually quite nice rock plot. If you want the one that I just showed you as well. This is a more typical one, right? Although in this case it's not rock. This is again not the typical rock plot. It does have coverage on the vertical axis, but here it has error per query. Yeah, and the advantage of using that is that you don't need to. You do that when you don't care about your negatives. Your typical bioinformatics search problem is the needle in the haystack type, where there's a few positives and lots of negatives. You don't care basically about all those negatives. Okay, it's like finding a restaurant in Amsterdam, right? You don't have to sample all of them. And you also don't need to find all good ones. You just need one restaurant, so it needs more for one day, right? And even if you go on holiday for 2 weeks in Amsterdam, well, you're already here in Amsterdam. If you would go for holiday, let's say you go to Paris, you need only 20 restaurants at most or so for a holiday. Yeah? Okay. So then it's much more important to have a good coverage, to find enough good ones, but you don't care too much about finding all the good ones.
Isn't that
Yeah.
isn't that the function of precision? Finding few homologs but good ones?
Yes, I'm not sure because I always mistake these things. And it was on the previous slide. Sensitivity, specificity, yes, oh, but precision. Precision is the most widely misused word in statistics because it means different things. Where's is it on here?
True positive or true positive plus.
Yeah, but that's one definition. Precision is oh sorry, no. Now I'm thinking about accuracy. Precision. One of these is precision, but I can never remember. That's why I have this in my
Selectivity.
Sorry.
Selectivity. The positive predictive value.
That's precision.
Yeah.
I would have to take your word for this because that's why in my lecture, maybe in the other lecture, I have this slide where all those terms are collected because I can never remember.
Precision or positive predictive value.
Yeah.
Isn't that like
That's
measured to capture?
Yes.
a
Yeah.
few-
True. Yeah. Yeah. True. Yeah. So if you can also plot precision versus coverage, right? And then you can see what is the best precision that you can get at any coverage. And so the highest fraction of correct predictions, which is hard to get from this plot.
Isn't it the opposite? It's the same like this one? Or is it-
No.
When this one is growing, the other one is going down. Because when
No,
there are
so precision goes up and down. Where's precision? Yes. So because this is the other ones, coverage and specificity, they are let's see it correctly. No, not this one. This one is a fraction of all positives, right? So that's a fixed number. So you can only make more predictions if you raise your threshold. So this can only grow. The same for error per query or sensitivity. That's on the whereas one-line specificity or error. That can also only grow. But the positive predictive value, is a fraction of this, which is what is this? True positives plus false positives.
Hits.
Hmm?
All hits.
All hits, yeah, all your predictions. So this number grows by necessity. If you raise your threshold, you'll have more predictions. Some of them will be true positives, others will be false positives. So this is your fraction of the true positives. This is the number of true positives as a fraction of all your predictions.
But error,
So-
how to say
If you take this plot, right, then this initially your position is not very, very good here. Because most of your predictions are actually false, they're errors. Here, your position actually starts to increase. But then you're starting to make more errors, then it goes down again. Yeah? Look up the slides for fundamentals of bioinformatics. It actually, has some examples of where it actually goes up and down. That's
But error per query is false positives over all positives. And
oh sorry.
precision is just true positives over all positives. So it's the same, just the opposite.
No.
Error per query is one minus specificity.
Yes, which is
No.
Oh, selectivity, I mean, sorry.
oh
Same,
right.
the same, just the opposite.
It's one minus the same.
Yeah.
Yes. Well, I'm not sure. I would have to look that up.
I think.
No.
Yeah.
Um,
Precision is 1 minus error per query.
Okay. But without slides, I'm not gonna. I'm not gonna try and explain that because I'm gonna mix things up horribly. Yeah. Oh, sorry. The magic button. There's. I'm pretty sure there's some confusion there, and but I don't know how to clear it up right now. Okay, so I'll leave this for what it is. Now. Yeah. What? Mess. Where am I? Right. Yeah. This you already know. Yes, this. I'm gonna skip this. So, because otherwise I'm running out of time. This is SciBlast, right? Iterative searching. I don't think I need to go into that. Jaap already covered SciBlast last time, right? Yep. Okay. But it's just the basic idea is to use the information from easy hits to find more difficult ones, right? That's the basic idea. Now, a different way of looking at this is to look at this as clusters of. So, if you think about transferring information on function of proteins, then you would actually like to have orthologs, right? You remember what orthologs are?
Homologs from different species.
Homologs from different species. Yes, but a bit more specific. So suppose you have you have an ancestral gene. You have an ancestral gene which is ends up in two different species, right? And then in this species it's actually duplicated. Then this ends up in two more different species, and these end up in two more different species as well. Right? So you start. So now we have. So which now are. So they're all homologs, right? That's easy because they all have the same common ancestor. Right? Which one are now paralogs? You say homolog in a different species, so that means you're saying so these are paralogs, but these are also paralogs, right?
No, orthologs.
Sorry, orthologs. Now I get it confused. Sorry. Okay. And then these are paralogs, right?
If duplication happened before the speciation event,
This happened after the speciation event, otherwise this one would have had duplication. Yeah? There's two speciation events here, or three actually. One, two, three.
yeah, like the last branching of species, in paralogs the duplication happened before that event, but in orthogonals happened after the.
Yeah, this happened after speciation. And what is it?
The last speciation.
What? No, this is speciation. This is a species tree, and here I have two genes which are also homologs. But then, so these one, this duplication happens somewhere over here, right? After this speciation. Now you have this species with two genes, two copies of one gene, and this one has only one copy. These are, the thing is, what you actually want, because what happens with paralogs in terms of evolution?
There's less pressure.
There's less pressure. So, well, there's one extreme case where you can actually lose one of them. Yeah? One is after duplication, one is lost again. but what often happens, or it actually happens also often, quite often, lots. But what also can happen is that they branch out to do different things, right? Which means, in terms of function, one of them retained the same function that the common ancestor had, and the other one is starting to do something different. Yeah? So if we call this function A, this one is function A, it's conserved. One of these has function A, the other one has a slightly different function. Yeah? So you can, so maybe this is function A prime, yeah? Or even more different, we call it function B. Now you actually want to know which ones, which one is the one that you, suppose you have, this is your query protein, you have functional annotations for these two proteins. You want to match it to this one, not to the other one. Yeah? Okay. So, so this is typically, there's different definitions of orthology, but this is a strict one where you say it's the homologue in the other species with the same function. It's certainly the most interesting one in terms of function annotation. Okay. So to do this, well, you can make clusters of orthologous groups, and how do you do that with a sequence search? How do you make a distinction between two good hits, but one is a slightly better hit? Well, you take the top one, right? That should be the best hit. But it can be more interesting if you have other orthologs, other hits here, right? So what you do in practice, it's called the bidirectional best hit, right? So you call two proteins a parallel. An ortholog. I always mix these two up. You call two. If you have a list of hits from two different species, right? Because it's never that simple. You have one query protein. You have hits from species A and from species B. You have a couple of hits. Now, which ones are parallels? Orthologs. Which ones are orthologs? Well, the best ones, yes. But from what? So what you do is you take this one as a query. You search in species B. Yeah. If you then get this hit list, right? Then you take the top one. And you query in species A. If this one also gives the original one back as the best hit, then you have the bidirectional best hit. Then you're happy. But if you get this, then you don't know. Yeah.
What happens in that case?
They can't assign an ortholog. Unless you've, sorry, I didn't see where the question came from. Unless you have other evidence that you can start using those. Or, if you're lucky, then if you take this one as a query, you do get the other one. Yeah? Then you're in business again. Right? It depends which query you started with. So your perfect case would be if this one matches that one, you find that one, take the second best, you find, and so on. Yeah, that would be. It's never that clean. This is biology. But if this signal is clear, then it's a good case for homology. This has also been done. It's in a database. It's already done quite a while ago, 97, and it's called clusters of orthologous groups. And it's all based on this bidirectional best hit method using signals. Okay. Now, yeah.
Isn't this also the same way? Sometimes you have to check if a closest homologue is actually existing. So, like, you go from, let's say, lion, alpha globin, you go to mouse, and then you have to check back. Because it could be that for the mouse, this is missing. So you check for the one that you find in mouse, and you go back and find something else in lion. So you just...
I'm not sure what your question is.
Or like, if you have one protein in human, but it's not existing in mouse, it's not in the database. So you go from human to something in mouse,
Yeah.
which is similar,
Yes?
but then you go from mouse back and you find something else from what you started with.
Yeah, like lion, so human.
Yeah, so then you see that this is on the database.
I'm not sure. I'm still not sure I get your question.
We can talk later.
Can we leave this to?
Yeah.
I'm sure it's similar, but
Yeah.
I can't map it right now. Okay. So this is like, and the real orthology is of course when you actually know which ones have the same functional role, right? But that's difficult to get. So this is like an operational definition of orthology based on the data that we do. One to think about, if we would, I'm not having enough time to go into it right now, but how do you can actually use this method also to find parallels, right? You don't have to make it twisted. Okay, so some problems that you that actually make homology searching difficult. Multi-domain proteins, low complexity regions, which is related to redundancy, short query sequences. This one is easy to understand, right? What happens if you have a very short query? You get insignificant heads, but why?
More probably.
Sorry?
It aligns more with more, more database sequences.
Yeah, but why?
If it's shorter, it's more likely to align with the random sequence.
Yeah, exactly. Well, it's more likely that if your database is big enough that you have a few small sequences that happen to be close enough to give a significant, or not as significant, to give a high enough alignment score, right? Okay, distance sequences, obviously difficult, and we'll go through these. Okay, so this is a Jaap's pet example of complicated domain architecture, but if you search for it, there's many examples like this. This is actually 3 domains, but in the sequence it looks like 5. Have you seen this one before already in the course? No? So it's pyruvate kinase, and so you can see that in the structure it's easy to see of the small domain at the top, big catalytic, I think it's the catalytic domain in the middle, and then the nucleotide binding domain at the bottom. This is actually the middle domain, if I remember correctly. This domain is actually 2 parts in the sequence. It's this. And then the top domain is actually the outer part. So what happened here? How does this evolve? If you search for it, you'll find this domain as a whole protein, and this domain as a whole protein in other species in the database. But here, there are 2 halves all the time. What happened in evolution? This is insertion, right? Yeah. So you start off with what? This one is the easiest to. Yeah. Then you insert. What color is this? Pink. Blue. I'm not good with colors. Then you insert the green one. This is green.
Yeah.
Right. So it just happens to land in the middle of this other protein. It probably landed hundreds of thousands of times in different places, and sometimes it doesn't matter. Sometimes it broke stuff. You get extinct, right? Maybe it landed 100 times in this other domain, but in the wrong place. Now finally it landed in the right place, or in a place where it doesn't hurt, right? You see here, the sequence starts here. This is the N-terminus. It has this single beta strand, and then it goes into the second domain, right? I think it's up to here. What was I saying? yeah, you can imagine that if you insert it over here or further down, you can't just insert it anywhere. Yeah, there's a couple of places where you can insert it without destroying the structure or something. And something similar happened to these. Now this is going to be quite tricky if you're doing homology search on this, right? Because in terms, what are the parts you want to find for function annotation? Well, all three. Yeah, you want to know how it's regulated, you want to know what it does, and you want to know where it does it. Yeah, you need to have all three matches. But if these matches are smeared over separated parts of disjoint parts of the sequence, then it's hard to get good hits on that. So there's actually, you can solve this iteratively, because which is the domain you're most likely to get good sequence hits on? The middle one, right? Yellow, I think. Yeah? So now you have good hits here. Okay, this is a domain. You don't know what to do with the rest. How are you going to search for good hits for the rest? You take it out, right? You get it out. Then you glue them together. So you uninsert it. Yeah? Then you do it again. Then you find good hits on this part, well, minus the yellow which you took out. It's my second domain. Yeah? Okay. Java actually has a method that's called domaination that does iterative searches on domains. Okay. Something else that can happen with multi-domain proteins is called, I think it's called chaining, where this is your query. You're interested maybe in the function of domain A, but you get hits on domain B, and then if you do further iterations, you get hits on domain C, which wasn't even in the query. Yeah. So SciBlast actually wouldn't do this because it will never consider C a hit. It just truncates it here because it only takes part of the lines to your query. It makes sense. But if you don't do that, it's not automatic. Okay. There's some more text on this which you can read at home. Now, low complexity regions. Why are those important? What does that mean, low complexity? Starting to run out of time. Well, you actually had a very nice example because I started this story with the z-scores, right? So how do you calculate the z-score? Well, you take an alignment of two proteins, right? One is your query, the other is your hit. You randomize your hit 1,000 times, different randomizations, and then you calculate the score and then see if your original hit score alignment is better than the randomized ones. Yeah? But what now if this was your query and this was your hit? It's a very good hit, right? All tryptophans, and your hit is all tryptophans. Well, but if you randomize them, you actually get the same score. Yeah, so now is it a good hit or not? Well, then you have to think about actually what assumptions there are behind this. But this is a low complexity region. Right? This is an extreme example. But it can be a little bit more subtle, something like this. And this has to do with structural features or functional features. There's different reasons why you actually get low complexity regions in proteins. That's a different story. But you can easily imagine that if you have something like this, which is only cysteines and proteins, that if there's two proteins that have a similar kind of region, there'll be a good match. But it doesn't tell you anything about what the function is. Yeah? Not necessarily. Okay. So you would like to have a method that measures this low complexity-ness, so you can filter it out and you say, okay, well, I'm not going to consider any hits on this part. In BLAST there's actually a setting, you might have seen it on the website, where you can turn on or off filtering for low complexity region. Another way you do that is hidden in this prose of Jaap. You look at the composition factor, count the number of each of the letters that you have in your alphabet, and then you count the number of ways you can reorganize that, and then you have to normalize it a bit. This is a bit difficult to follow. So there's also an example. So let's say you have this small sequence. It's a DNA sequence. How do I know that? Because n equals 4, n is the size of your alphabet. 4 alphabet of 4. So A, T, T, A, T. Then length is 5, and my composition is as follows. I have 3 T's, 2 A's, and none of the others. Yeah? So now I can actually make a frequency vector, that's this R, and so this is the number of times I find a letter 0 times. So there's actually 2 of those. The C is 0 times, the G is 0 times. This, the number of times I find one letter once, none. Twice, that's 1, that's the A, and 3 times, that's the T. And then I find for nothing 4 or 5 times, right? So now I take the product of the faculties of these numbers. Where is it? Sorry, no, the product of the faculty of these frequencies, so 3 and 2, right? Which means that there's 3 faculty times 2 faculty, that's 5, no, that can't be, oh sorry, I'm going too fast. So, let me take one step back. What am I trying to calculate here, right? The complexity of this region. So, what is the most complex sequence you can have? That's one where each position is unique. Right? Each position has its own letter. Well, if you have 5 positions and 4 letters, you can't even do that. But if you would have A, C, T, A, C, G, T, for example, then that's already fairly complex, right? You have lots of different letters. If you have lots of different letters, there's no, sorry, let's say that. Yes, if they're all different, then it's easy to calculate how many possible orientations you have of 5 letters, right, or 5 positions. That's the faculty of 5. What I want to know is how many ways there are to make this. So to do that, you actually have to divide by the arrangements that you don't care about. Because if you have 3 T's, then you can swap the T's, but it doesn't change your sequence, right? So that's a 3 faculty. So you take 5 faculty because there's 5 faculty ways in which you can organize 5 things, right? 5 times 4 times 3 times. There's 5 places to put the first thing, times 4 places to put the second thing, and so on. Yeah. But you don't care whether when you swap the T's, you don't care when you swap the A's. So there's 3 faculty ways in which to reorganize the T's, which is 6. And there's 2 faculty different ways in which to reorganize the A's, which is only, you have 2 A's, you can only swap them once. Yeah? And 5 faculty is 60 divided by, no, sorry, that's, I don't remember. This is 10 times, it turns out there are 10 different ways to get a sequence of the same composition, not, how to say that? Yes, there's 10 different ways in which to write a sequence of A's and T's where you have 3 T's and 2 A's. Yeah? You don't care about the order. But you also don't care about whether this is an A or a C, because CTT, CT is not more or less complex than ATT, AT. Yeah? So that's the second product where you use, so here you use those numbers, here you use the other numbers where you don't care about which letter they are, or only how many there were. And that says there's 12 different combinations of letters that actually gives the same complexity, and then you take the product of those. So then you get that there's 120 different sequences that you can write down with 2 of one letter and 3 of the other letter. But you don't care which are the 2 letters. Yeah? it could be 2 C's and two A's and 3 T's. It could be 2 T's and 3 A's, or 2 C's and 3 G's, or 2 G's and 3 T's, or whatever. Yeah. 120 slightly too many to write them all down, but I think you can get it. Okay, so that's what actually was on the previous slide, but then now here it's still what's the word for it? It doesn't matter. Here it's concrete, not concrete in the previous one. And then you normalize this by, so this here is the 120 again, by 1024. What's 1024 in this case? Yes, you could say that, but there's a simpler way to say that. If you have a sequence of 5 letters and there's 4 options for each letter, how many different sequences you can get? 4 to the power 5, which is 2 to the power 10, which is 1024. So this is the number of possible 5-letter sequences in a 4-letter alphabet. Yeah. So this finally your low complexity score is this number, which is the fraction of all the possible sequences of the same complexity that we calculated here, divided by all the possible sequences. Yeah? Now you can imagine how the higher this is, the less complex your sequence is, because it's sort of, well, you would always get it with this mix of things. Right? Yeah, makes sense. Okay. There's a few pages on this in the book as well, if you want to look up the details. There's actually, so this is used by BLAST to filter out low complexity regions with some threshold that I actually don't know exactly how to say it. There's also separate algorithms that use these methods to calculate the low complexity regions. There's still some logic that you need to apply, because how are you going to select which part of the sequence to look at? You need to have some windowing schema also on top of this, which we're not going into now. Okay. Oh yes, it's mentioned. Okay, so redundancy is about the database, typically people use what's called the non-redundant database, the NR, so that just ensures that there are no real duplicates in there. But you can still have redundancy in the sense that for some proteins, like flu virus, there's like millions of very, very close homologs. They're all single or 2 or 3 amino acid differences, because that's what these viruses do. It's similar for HIV. There's lots of variations that only have very, very small sequence differences. Which is going to be difficult for your search if you're not particularly interested in those viral hits, but you want to actually see hits from other species as well. Yeah? So you want to be able to filter it out. So how would you do that? Well, you don't filter on identity as the NR does, but you filter at a lower threshold of percentage identity. There's actually an NR70, which you can also download from